In this lecture segment, we'll be looking at one of the most important resources on the planet, that of water. You should be reading Chapter 15 and reviewing that text along with the lectures here. To begin, some terms we'll use and distinguish these from one another. Fresh water is that water that we consume. It has few dissolved ions, such as various salts and minerals. Conversely, wastewater is that which has been used and is contaminated by water released after use by households, industry, or agriculture. It can contain a wide variety of different contaminants, organic, inorganic, or sediment and physical materials. Surface water is what you're probably most familiar with. It's any type of body of water or channel of water found above ground. This includes oceans, although we won't be spending much time on the oceans themselves, rivers, and lakes. Water provides a wide variety of ecosystem services to both animals and plants provide significant ecosystem services with regards to cleaning water and making it potable for human use. Humans, although we're 75% water by mass, we require fresh water, despite the fact that our internal bodily fluids have a wide variety of dissolved substances. Where we get that water typically has been from freshwater sources such as lakes and rivers, but as California grows in population and its finite water resources are insufficient, various new schemes of converting gray water for use in landscaping irrigation has been tried, and more recently small communities in California have examined the notion of treating sewage water to create a source of drinking water. And despite the fact that this can be done technically fairly readily, there's a huge, as you might imagine, consumer barrier in terms of being able to trust that that water is safe to drink. This points up the difficulties we face in ensuring adequate water supplies in the future, especially in arid places like California. When you look at the Earth as a planet, about 75% of the surface is covered by water, largely as the oceans. However, only about 1/100% of that water is directly usable by humans. And most of the water that we see on the surface that's not in the oceans, over about 80% of it, is trapped in permanent ice in the ice sheets in Antarctica, Greenland, and on glaciers throughout the northern climates mainly. Water moves through the water cycle, moving between gaseous and liquid and solid states. The water cycle should be a review topic from the standpoint of earlier science courses, and I'm going to leave you to spend most of the time reviewing any of the terms that are not familiar or you don't recall. But suffice to say that evaporation takes water into the atmosphere, precipitation returns it, and over land areas with significant vegetation, transpiration is the movement of water from liquid to gas state mediated by plants. Water infiltrates, moves through or over the soil, can pass through rivers and streams, and ultimately makes its way back to the oceans. You should be familiar with this process, or all of these processes, for the purposes of quiz and exam questions. It's somewhat staggering to note that a huge amount of water is transferred through the water cycle. 17 trillion gallons in the book's estimate are processed as water vapor. The process of condensation creates clouds, and then ultimately certain conditions are met. Clouds generate rainfall or snow that returns back to the earth, and ultimately most of this water will make its way back to the oceans, and along the way it can be taken out in rivers and streams, lakes, for human use. I think it's common sense for most people that the ocean itself, seawater contains high concentrations of salts and is toxic in any significant quantity consumed by humans. It's also toxic to plants, and saline waters are oftentimes frustrating in that they're available in areas, especially arid areas, but can't be used for irrigation or human consumption. We get most of our water as humans from lakes, rivers, and also groundwater reserves. The problem is that the location of human populations and where these rivers or these sources are located are not necessarily close by. In developed countries, there's been large efforts to transfer water by canal with reservoirs as storage. But in many developing countries, water scarcity is a serious problem because humans cannot live without it, but aren't necessarily able to live always right nearby where it's available in a drinkable source. The World Health Organization has documented this, that approximately 2 billion people on the planet, or 1 in 3, lack sufficient access to clean water. And those are areas where there's physical scarcity, in arid areas, or areas where the quality of the water is poor. And some of the areas that currently have adequate water are facing changes and reduction in water supply through climate change or growing populations, to the point where in the future this is anticipated to be a growing problem, because not only is the water needed for human consumption, but also for agricultural purposes. So with population growth, approximately 2/3 of people may face water shortages by 2025. In the United States and in California, we face droughts, but are able to manage those with minimal disruption of our lifestyles, other than restrictions on watering lawns or washing cars. So far, our access to water has not been particularly difficult. So if we get a lot of our water out of surface water bodies, both rivers and streams, if we pull too much out, pump too much in for human use, we overdraw the surface water account, so to speak, and this can result in both shortages of water in the stream and reduced flows, which can affect downstream users, fish populations, or other parts of the natural ecosystems. And these ecological effects can affect anadromous fish, streamside vegetation, and wetlands. If you look at estimates of the percent of surface water in use by the year 2000, this is from just prior to that time, you can, as you might imagine, the arid and hotter parts of the United States are at greatest risk to be using the most of the available water, in some cases overdrawing it such that rivers and streams are drying out. But these areas are potentially at risk of growing based on changes in climate that may occur with global warming. Rivers in many cases are going dry. The Colorado River virtually ceases to flow about the point at which it reaches Mexico, when it used to flow into Mexico due to extractions in the southwest and upstream in mountain states for a variety of agricultural, municipal, and other purposes. The Yellow Sea in China has experienced water shortages and gone dry at the lowest reaches. And a very striking example in the Aral Sea in Central Asia is shown here, where if you look at the borders in the lower figure, by 1860 in the yellow there was a fairly large continuous lakeshore. By 1998 that had reduced down to the smaller area, and it was predicted to fall even further by 2010. And a recent photo shows that the predictions of the further drying to be fairly accurate. So the drying of rivers has implication for inland seas and lakes depending on the local drainage network. This has implications for wetlands, which are very important biologically, and the fact that they store water and buffer floodwaters by spreading water out, and can take up contaminants out of the water and actually serve as a filtering mechanism. But as overpumping of water out of streams and rivers goes on, then these reduced flows can reduce the water availability to wetlands and dry them out, and they lose their biological value in many cases. Groundwater is subsurface water, which we'll talk about, can also be pumped faster than it's replenished. The Ogallala Aquifer, which is one of the largest aquifers in the United States, is shown here in pink, just east of the Rocky Mountains. This area, a subsurface sandstone formation, contained tremendous amounts of water, but most of this water was introduced into the ground following the end of the last ice age. With changes in climate and increased pumping for agricultural use, the water levels are falling. So as the water is deeper underground, it costs more to pump it, and there can be conflicts between wells and diminished returns as far as being able to sustain the production for food supply. In many cases, there are connections between rivers and streams and wetlands, with shallow groundwater especially. So as groundwater levels fall, the connection in the subsurface declines, and the subsurface replenishment of those streams, rivers, and wetlands is also reduced, and they may go dry as well. With extreme levels of pumping, land can actually subside or sink, and this can cause disruption of power lines, pipelines, roads, and other solid infrastructure on the ground surface. In coastal areas, pumping too much fresh water can cause seawater to flow into the subsurface and create contamination such that the water can no longer be used. Sinkholes are very prominent in the news sometime and can actually devour whole houses or more. In the larger scale, in the picture on the right, this is the San Joaquin Valley floor that in 1925 the ground surface was up at this upper marker. Over time, due to pumping and reduced pressure supporting the ground layers, the ground level has gradually sunk to the point where, as of 1977, it declined by up to 25 feet. So serious problems occur both in surface and subsurface waters when we pump more out that has been replenished through rainfall and snowmelt. This goes back to the notion of natural capital and natural interest, in that the interest is the amount of water coming into the system each year, and to withdraw water beyond that is to invite serious consequences. This concludes the first part of the lecture. Should move on to part 2. Now we turn to some of the major water use issues we face, especially in California and the western United States. These revolve around land use such as agriculture, climate change, water use efficiency, and water quality, which we'll treat more in the third section of the lecture. California, especially Northern California, gets most of its incoming precipitation in the form of snow, largely in the Sierra Nevada. Approximately 80% of the water that California manages comes from that snowpack. And as you can imagine, if global temperatures are increasing, that snowpack will be diminished and more precipitation will fall as rain. And the problem is that the current system of reservoirs and canals that move water around are devised for a snowpack dominated regime, where water is stored in the form of snow over the course of the winter and gradually released into the start of the growing season. But coupled with that is the fact that 2/3 of the state's water is generated in Northern California, whereas about 2/3 of the population is in the southern part of the state. Thus there's a need to convey and move tremendous amounts of water from the source areas in the north to the major demand areas in the south. Unfortunately, it's very expensive to supply water to the south in terms of being able to put water into canals through pumping, and then one of the largest electricity uses in the state, if not the largest, are the pumping plants at the southern end of the San Joaquin Valley that pump water up over the Tehachapi Mountains. And as you know, California is prone to major earthquakes, being very tectonically active, and these could break the rigid system of canals and pipes and levees that protect a lot of the water systems at great cost and great risk to interruptions in supply. With growing demand, due to growing population in the state, which is projected to grow by many million more over the next few decades, the supplies in California are not going to be sufficient to meet the future needs. And thus desalination has been proposed from coastal waters. However, it's very expensive in its current technology, and the biggest problem we face with it is it has enormous energy costs to remove the salt from the water under current approaches. So supply is a major problem, and maintaining these supplies and routing the water around are huge challenges for California over the next few decades. In many places around the country, not just in California, there's an increasing reliance on groundwater, and these groundwater resources are derived from aquifers. These are large underground areas of rock or soil that both store and transmit usable quantities of water. There are many places on hillsides and other areas where the ground is saturated with water, but they're so small that they can't be readily used for management purposes. So aquifers are for the most part considered large bodies of subsurface materials that can store and transmit manageable amounts of water. In the document, or excuse me, in the figure you'll see on this slide, you'll notice that there are different layers, unconfined aquifers that rise and fall with inputs of water and pumping, confined aquifers that are deeper and under pressured systems, and all of these can interact with and be affected by saltwater intrusion, but most prominently in the shallow unconfined zone in coastal regions where overpumping may lower the saturated zone such that the higher water level in the ocean will cause water to flow inland, and that can affect domestic wells, agricultural wells, and essentially eliminate a supply if it becomes contaminated with salt water. So groundwater management, although useful as a supplement and as an expansion of water resources where water can be stored and then taken at need, is also prone to management issues as far as maintaining its long-term viability. In coastal areas, especially in the Santa Barbara region, San Diego, and other larger population areas, it was noticed that salt water was infiltrating or flowing into these coastal aquifers and causing that water supply to be at risk. One of the major responses was to build a branch of the California Aqueduct over to the Santa Barbara area to bring in surface waters from outside the region. And this is typically what's been the approach in the past, is to supplement limited local supplies in coastal areas with imported water transported over long distances. Another issue that's gone on that's probably most noticeable in Southern California is that when you think about the number of people living down there, the amount of wastewater generated and treated is discharged to local streams and rivers, and even though it's not unsafe or unsanitary, it is a large quantity of water that, when added to rains and things like that, can actually increase the flows to the point where flooding can occur in places like the Santa Ana River. Dealing with water and wastewater, which we'll cover in the water quality section, part 3, one of the issues that's been dealt with effectively so far in the town of Arcata on the north coast took a landfill area that was no longer used and constructed a wetland over the top of it, and then allows water from the sewage treatment plant to spread over that, and then the plants and organisms in the wetland do a final polish and cleanup of the water and further improve its water quality before it's released to the local bay. And this is a much cheaper, much more effective way of treating water than alternative chemical processing in terms of the amount of industrial and energy and chemical intensive processes that have to be used in a treatment plant. So wetlands as a part of a treatment system are probably increasingly going to become important from a water management point of view. The water shortages we face are going to involve trade-offs, and in some cases there are still proposals to build new dams, large dams in some cases, and creating reservoirs, but the amount of water that's stored behind the dams in the reservoirs is offset to some degree by losses to evaporation, especially in hot climates like California. As an alternative to building new dams, especially in places where it's hard to find the land area that can support them in the landscape, Orange County found that there was a less expensive approach by invoking a greater emphasis on water conservation. Because if you can increase your supply by consuming less, you can do it at a much reduced cost. In the state of California, for example, about 80% of the water that's consumed for management purposes is used for agriculture. About 15% for urban, and about 5% for other industrial and miscellaneous uses. So agriculture, and being the dominant water user, is the place where the greatest benefit or savings can occur with an investment in water conservation. Irrigation methods that use less water, drip or advanced sprinkler systems that reduce the amount of wasted water have shown to be very effective and cost-effective to farmers and orchardists in reducing runoff, which can carry chemical waste off of fields, and also just simply using less water and reducing the cost of purchasing water. So it's important in this diagram in this slide to look at the water cost associated with various types of foods. You'll notice that beef, for example, uses an enormous quantity of water compared to vegetable and fruit products, but is even much higher than pork or chicken among the different meats. So the ecological footprint and the water footprint of beef is extremely high. Likewise, if you think of the just the water it takes to produce even a plastic water bottle, several gallons of water are required to make a single bottle of the drinking water that you may be purchasing at a premium. So there is a water cost, like an energy cost, in most things that we consume. Likewise, consumer products, clothing, a ream of paper, cotton shirts, things like that, all have fairly high water costs associated with them. And while these aren't disclosed, they are worth investigating and thinking about in the context of making consumer choices. Just as in the earlier lecture talking about interface carpus, many industrial programs and water use systems are looking at ways to reuse water instead of discharging it and using fresh water in their processes. This water use efficiency, likewise, has become much more common and even required in household applications, in that low-flow toilets are required in many places, and water-saving shower heads and faucets and things like that are increasingly becoming required to further minimize the impact of urban water use. It's been noted that while Southern California's population has grown, the total amount of water consumed has remained roughly stable up till now, and that has been due to the increasing application of urban and residential water-saving devices. But it's, again, as noted in the last slide, if we consume less products, less materials, will use less energy and will also save water, because both are required for the production of most consumer products, if not all. This concludes the second part of the lecture. You should proceed now to the third part on water quality. In this lecture, we turn to the problems associated with water quality. Previously, when we talked about water availability and general water issues, we noted that the degradation or pollution of water to the point where it can't be consumed can reduce it as an actual resource for consumption. There are several different categories of water pollutants and different processes involved. Some, like the picture shown here, with the acid mine drainage materials moving through an eastern deciduous forest environment. Urban environments where trash and other urban pollutants wash in are probably fairly readily recognized. What may be less intuitive to you is when you see images of smokestacks emitting pollutants into the atmosphere, you might think of these only as air pollution problems. But bear in mind that the chemicals and particulates that are contained in those air emissions regularly come back to Earth in the form of precipitation. And we'll talk about some of the impacts of those as well. As a general term, water pollution refers to any situation where there's an addition of a constituent that might degrade the quality of the water. A particular category that's of common concern in most cities, and especially growing urban areas, is stormwater runoff. This is a situation where precipitation encounters the surface, typically paved or hard surface, and runs off over the surface of the land into storm drains or such, but can carry with it pollutants, chemical or physical or other types. Stormwater runoff can occur is most commonly thought of in urban areas, but could also occur on agricultural lands or other places where there's significant surface runoff. One very important idea to bear in mind is that water pollution is closely tied to the sources, and the sources of pollutants are typically correlate fairly well with certain types of land use. You wouldn't expect industrial pollutants to be coming off of farms, and likewise farm-related chemicals would probably not likely come off in great quantity from urban areas. So land use and water pollution sources are very closely tied. Within that, there are two distinctions made in terms of types of water pollution sources. First is a point source. This is a discharge pipe or a specific outfall. It could be the wastewater coming out of a factory or sewage treatment plant. In contrast, there are what are called non-point sources. These are dispersed, broad areas of land where pollutants are washing off large areas of the landscape and aren't coming out of a particular manageable source. In the diagram here, you'll see that the non-point sources are things like agricultural lands, croplands, can be city streets, rural homes, suburban developments. Those are typically going to be your non-point sources. Further down, you may have point sources with, like I said, pipe outfalls from factories or wastewater treatment plants. So it's important to bear in mind the source type and the land use associated with different categories of water pollutants. Pollutants move in a couple of major different ways depending on the type of constituent they are. Some pollutants are dissolved in water. Picture table salt dissolving in water to where it's no longer visible as a separate compound. It's dissolved completely in the liquid. Other minerals may be examples of that, and nutrients such as nitrate coming off of fertilizers and such. They break down into ionic materials and then they form clusters with water molecules and then move completely with the water. In contrast with soluble substances, there are non-soluble constituents. These are things like oil and other organic liquids. Solvents may be one example, to where they dissolve only very poorly and typically will stay in their native form, undissolved in water. And they may move with the water, but they can move as distinct liquid. Picture a drop of oil on water, and the oil moving with the water but staying separate from it, not dissolving into it. And finally, there's sediment and other forms of particulate material. These can be typically soil materials, sand, silt, and clay, mineral particles, but could also include fine organic fractions of, say, broken down leaves and litter and plant materials. The term watershed is one that you may have heard before. It's an area that contributes flow to a particular point of observation on a stream. It's easiest to visualize with a map or other physical map representation. If you picture the ridge line surrounding a point of observation, say at the mouth of the bay, any rain falling on that surface, if it were to run over the surface, would flow locally into streams and rivers, and then through the stream and river networks down into the larger rivers, and then ultimately enter into the point of observation, which in our case, in this example here, might be a observation point at a bay. Again, this is tied predominantly to flow of surface water, and groundwater may behave differently. But for the most part, and the most common situations you'll find, watersheds, surface watershed borders also reflect where groundwater is moving as well. So watersheds are very important and a useful concept to manage water, both water quantity and water quality, as all the processes in land areas that are affecting the movement of water and also its quality. This is the watershed idea has become a very common and dominant way to manage water resources in most places in the United States. When you look at the different types of water pollutants, especially in the United States, one of the most common causes of water pollution is from pathogens. These are disease-causing microorganisms. Sometimes they can include viruses, and they're typically released from industrial and agricultural waste. In coastal areas, you'll find beach closures. Even though it's coastal, they get lumped into this category. And the introduction of bacterial waste can cause human health hazards, especially, of concern. So if there is a degradation or an impairment, either temporary or long-term, in the United States, these pathogens are the most common cause. Other categories that are important are metals, and this excludes mercury, which is more of a toxic, is treated separately because of its extreme toxicity. Nutrients, hypoxia, which is the loss of oxygen for a variety of reasons. If waters become oxygen deficient or lose almost all their oxygen, then aquatic life and fish will suffer or perish. PCBs, polychlorinated biphenyls. These are used in light transformers, especially the ballasts, at least the older ballasts that used to be in fluorescent lights. They're a fairly toxic substance. They've been greatly reduced in quantity, but they're still out in the environment. Sediment, mercury, high pH or low pH, and pesticides. So these are some of the main reasons why a surface water body is declared to be impaired or polluted in the United States. And again, some of the actual pollutant types, these aren't necessarily the categories, can include industrial chemicals, raw sewage, or only even partially treated sewage, which contains the pathogens, garbage coming off of litter and things off of urban areas, oil and other petrochemicals, fertilizers, pesticides, and mercury, both from mining, historic mining uses, and from industrial waste, and more recently from increased combustion of coal, which contains trace amount of mercury in its biological origins and geochemical formation. And the combustion of coal in large quantities globally has increased the amount of mercury into the atmosphere, that when it's coming back to Earth, it's ending up in water bodies and fish and other aquatic organisms at levels that are considered hazardous. Coming back to the point source pollution, these are probably the earliest ones that were recognized, going back into the early 20th century, and with the advent of modern water treatment plants especially, there's been an extensive system going back to the Clean Water Act in the 1960s that require dischargers to obtain permits and monitor what they're releasing to surface water. And typically, if these may be coming out of actual sewage treatment plants, but even if it's a factory or other point source, there's typically some sort of requirement that the discharger treat the pollutant that's coming out to the point where it's removed and not causing contamination problems downstream. So point source pollution systems are somewhat more readily identified and managed because they are typically associated with some sort of facility or installation to where some sort of treatment system is at least more readily employed. The case study that the book focuses on in the case of water quality is the Chesapeake Bay on the eastern coast. It's the largest estuary, or zone of mixing freshwater and seawater. In this case, it's on the Atlantic coast and mixing with freshwater coming in from the eastern states. It's in the middle of an area that's some of the most densely populated areas. It's complicated by the fact that there are 6 different states and the District of Columbia that discharge waters, storm runoff, effluent from sewage treatment plants and such into the bay, and not to mention have a wide variety of land uses on the ground and the watersheds surrounding the bay. So Chesapeake Bay faces enormous challenges and has had severe water quality problems over the last few decades to a century. Zooming in a little bit, it's again centered in around Baltimore and most of the areas in Maryland, but the areas drained include the other states as well. In the bay itself, a number of fish species have crashed. Their populations have diminished dramatically. Oyster beds, a popular seafood item, have disappeared, and the populations have diminished dramatically. And in the bay itself, there's been large growth of algal blooms. And as these aquatic plants grow, they consume oxygen, and then the waters can become oxygen deficient or devoid of oxygen in some cases, in some smaller areas, and virtually all aquatic life will perish. So there are just a few of the major water quality problems that are associated with this estuarine system. Most of the problems that we noted there and others have been tied back to more of a non-point source situation where you've got runoff coming off the landscape, carrying with it wash from agricultural lands, picking up nutrients and pesticides. In urban areas, lawn chemicals have been applied, and then city streets pick up a variety of different types of chemical constituents from automobiles, pet waste, and things like that. So there's a large soup, if you will, of different types of contaminants coming into the area from these varied urban areas to rural and suburban areas and agricultural lands. When the runoff pollution flows into the bay, especially under higher rainfall-driven events, excessive amounts of nutrients come in, and as we noted, that can lead to algal blooms. And when algal blooms become elevated and grow too large, this is an example of the process of eutrophication, or over abundance of and production of green plant life. The nutrients feed the algae grow, they consume the oxygen, they block the sunlight from reaching other plants underwater, and you end up having a variety of different types of organismal death in the water. And again, the deficiency of oxygen when the underwater plants die can lead to the hypoxia, and then you have essentially dead zones forming within the bay where they can no longer support life. Dead zones are well known, unfortunately. There's estimated there are as many as 350 worldwide. A very prominent one that's been in the news periodically is a dead zone off the coast of Louisiana, tied into discharge from the Mississippi River and other coastal waters. And again, this especially with the Mississippi, which carries and drains an enormous quantity of agricultural lands in the center part of the country. This area with elevated nutrient loads has created these algal blooms that have created large-scale hypoxic oxygen devoid zones and a massive dead zone off much of the coast in this area. And it's a very difficult problem because the continued agricultural activity is an ongoing source of nutrients that feeds these algae. In the Chesapeake Bay example, though, it was determined that the primary problem was that the nitrogen coming into the bay was related to synthetic fertilizers, put in primarily being put onto the surrounding agricultural lands. There are, however, you should note, atmospheric sources coming into the site as well, and we'll talk about those. But when you look at the inputs and outputs by watershed type, you're finding that more of the nitrogen coming in from the landscape to the bay was coming in from agricultural than either suburban lawn, landscaped areas, or certainly the forest. Forest areas in general tend to consume and hold on to, for plant growth, all the nitrogen they can get. They release a fairly small percentage of what they take in. Landscaped areas and suburban developments, and also in agricultural lands, have a tendency or a risk of being over-fertilized. And it's this fertilizer release that was again attributed to causing the pollution types in the bay. As we noted, though, there are atmospheric sources, and this goes back to the opening slide with smokestacks, that when you have chemical constituents being emitted into the atmosphere through combustion or releases through smokestacks, these chemicals, such as nitrogen oxide, can go into solution with rain and moisture in the atmosphere and come back as acid rain. They can also go into chemical reactions to where they can be then reintroduced into the watersheds and ultimately places like Chesapeake Bay as nutrients, and they can lead to nutrient pollution. Not focused on here is the example closer to home of Lake Tahoe. Lake Tahoe has had severe problems of undergoing eutrophication or excess of algal growth due to nutrient pollution historically from within the Tahoe Basin, but now it's believed that one of the largest sources of nutrients affecting Lake Tahoe is car exhaust coming out of the Sacramento area and the Bay Area. Overall, nutrient pollution is the leading type of water pollution on a global scale, according to the United Nations. This section of the lecture on water quality has been split into two parts, and you should continue now on the fourth part of the lecture. We continue now with our discussion of water quality, and I want to remind you to be reading Chapter 16 in the textbook for this material. As we noted earlier in talking about the Chesapeake Bay example, a number of water bodies across the United States face the same problems. And again, it goes back to this idea that water quality problems are tied to land use, and the land use carries with it certain types of chemicals and other constituents that can degrade water quality. In urban areas, and in actually a lot of the United States, our infrastructure is aging. And this is particularly problematic with things like sewer pipes, which will corrode and degrade over time and eventually start leaking. And this is a source, a fairly common source, not a massive one, of sewage releases to local streams and rivers, and is not at all uncommon in coastal areas to cause beach closures. But in other parts of the country, in urban and industrial areas, there are also toxic pollution releases coming on from small industry, from large industry, and these discharge pipes, although monitored and regulated, oftentimes do release materials into local waters. And the smokestacks pervasively are still releasing chemical constituents that can lead to acid rain and affect water quality in places like, especially in the Northeast and the Atlantic states. A more recent addition to water quality, although not of widespread massive concern, is that there are drug residues, especially chemotherapy drugs, which are very, very resistant to breakdown, and that's part of their, I guess, their chemical effectiveness, can be persist through the wastewater treatment process to the point where they're affecting water quality life. You're getting mutations and in some cases declines in certain population due to modern pharmaceutical chemicals. Just as a reminder, point source pollution is dealt with through a process of permits and monitoring and typically some form of treatment. We turn now in a little more detail to non-point source pollution and options to control this type. Again, because it's a landscape scale process, pollutants coming off large farming field areas or orchards and such, they're much harder to control at single locations. Instead, a major distinction between point source and non-point source is that non-point source pollution regulations based on the laws, water quality laws, emphasize the use of what are called best management practices, or BMPs. These are meant to be practical but effective pollution prevention measures that can reduce the amount of chemicals or sediment or other pollutants reaching waters. A common one that you'll see around urban areas is surface erosion control. When you see new construction, oftentimes it'll be down on bare soils, and the soils can be affected by rainfall and surface erosion, and the soil and sediment can wash off into local storm drains and ultimately local streams and rivers. So surface erosion control, putting up ground cover, putting fabric filter materials around storm drain inlets, are types of surface erosion control properties or practices. In agricultural areas, shelter belts, strip cropping, and especially buffer strips are very effective ways to reduce the amount of chemicals, sediment, and other pollutants reaching local streams and waterways. The surface erosion control, here's some examples from construction sites where you have silt fencing along an area before it drops off into the river or stream. There are also these what are called wattles, or hay rolls of hay woven into tubes that protect the inlet storm drains from any kind of surface washed off materials. Water passes through this, is filtered, and sediment especially and other materials are trapped before they enter into the storm drain and ultimately the streams and local rivers. Agricultural practices such as buffer strips. These are very important and are used not only in agricultural areas but in forested zones and even in urban areas to some degree. Are places where native vegetation is left intact along streams and river. And so as you can imagine, if you have sediment flowing off of a landscape, erosion coming into this, it can be trapped and filtered. Likewise, some chemicals can be taken up by the vegetation as they reach this zone before they enter into the creek. Another term for these are called filter strips, as an old term, but that was primarily due to their focus on filtering out sediment before it reached this. But buffer strips are very effective and very important process or best management practice. Not only do they help protect water quality, but they help maintain native ecosystems along the creek and help shade the stream and protect cooler water temperatures where local fish and other aquatic species may require that. A large program of best management practices were identified and put into practice to reduce the pollution, especially the non-point source pollution that was impacting Chesapeake Bay. Each one of these is based on a goal of reducing pollution at the source, a strategy, and so on. And so there's a whole system of regulations and guidelines and practices that are fairly detailed in terms of their attempt to improve water quality. And again, it's not only pollution reduction, but restoring habitat, protecting the watersheds, and so on, and that the local areas have fairly significant control over the specific ways in which these best management practices are employed. And that's very important from the standpoint of engaging people to follow the practices. In most cases, best management practices are voluntary. They're listed, recommended, but they're not necessarily rigorously enforced. Water quality violations can bring fines and other sanctions, but typically on the prevention side at this stage, in most cases, the attempt is to keep it on the voluntary side from the watershed landowners. One of the major goals, as we noted of the Chesapeake Bay situation, was to reduce the amount of nutrient loading, and the program, the Chesapeake Bay program, has focused on trying to educate farmers in the use and application of fertilizers and the maintenance of animal waste from feedlots and other forms of animal holding facilities. There have been some successes with this, in that a lot of the nutrients, as much as 50%, have been reduced through changes in practices on the farm and on animal facilities, and then coupled with buffer zones or the buffer strips along the stream has had a very successful impact on reducing major nutrient loading to the bay. The buffer program, or excuse me, the Chesapeake Bay program, as we noted, takes advantage of managing riparian areas. These are the streamside areas near the streams and rivers that flow into the bay, but also lining the bay itself. And the forest buffer zones, over 2,000 miles of those have been established, and these constitute those buffer strips shown earlier. Another practice has been with residential areas, trying to educate landowners and homeowners to not over-fertilize their lawns, and where possible to plant native plants that don't need as much fertilizer application as, say, more exotic ornamentals. Another regional effort of the Bay program has been to focus on the air pollution standards to try to minimize the loading of constituents and nitrogen compounds and others that reach the bay through air emissions and return through precipitation. This is again part of a larger effort to make a more sustainable society and one that creates less waste. And in this case, the waste, both in terms of its entry into the atmosphere, has significant impacts on water quality as well. Unfortunately, even with all the effort that's been done to date, Chesapeake Bay is still facing problems, especially episodically under very wet years. A lot of wash occurs, and chemicals and sediment and things are still reaching the bay and causing problems, and you're still losing aquatic life. So it's an ongoing struggle, but one that probably will persist as gradual population growth occurs in this area. Before we conclude, just want to point out two problems associated with groundwater contamination, of which there are definitely others. But two of the more common ones, and you might actually observe these, either have or may well in the future: leaking underground storage tanks at gas stations. Historically, gasoline was stored underground for safety purposes because it's a large volume of flammable liquid. Keeping it underground is definitely safer, but the metal tanks that were used historically corroded, and by the 1980s there were widespread leaking underground storage tanks virtually everywhere. Almost every tank that was underground for any length of time was leaking. This led to the advent of the modern environmental consulting industry, where companies formed and grew to oversee the cleanup investigation of these sites. Since that time, there has been major improvements in the technology. Gasoline storage tanks underground now are double-walled and clad in fiberglass and other materials to reduce their corrosion. There are better leak detection monitoring systems and much greater emphasis on prevention of contamination of groundwater by gasoline, diesel fuel, sometimes oil storage tanks and things as such. They still do leak, and ironically, one of the major additives added to gas going back into the 1990s to improve air quality, MTBE, which was very effective as an oxygenate in creating a cleaner burning gasoline type. Unfortunately, the MTBE caused leaks in gaskets and seals, broke down materials that were in the piping and plumbing system, and caused a lot of reintroduction of gasoline back into formerly cleaned up underground storage tank facilities. Most of these have been addressed, and the systems have been corrected. There are still ongoing investigations and cleanup dealing with that, and in some cases MTBE has been removed from gasoline to be replaced by other compounds, but using gasoline and other petrochemicals in around our transportation system creates ongoing threats to waters, both groundwater and surface water. And finally, if you think about everything that goes into a landfill, all the different things that you throw away or you've seen thrown away if you've gone to the dump, all of that material, while covered with liners to some degree and buried under soil to isolate it from the environment, historically has still been connected to the hydrologic cycle by virtue of rain infiltrating through the soil cover into the waste, and then causing chemical reactions that will dissolve and cause the transport of those chemicals. Leachate is the general term for waste-containing liquids that come out of landfills, and that leachate can be fairly toxic, sometimes just unhealthy to drink, but so varying degrees of toxicity. But it is an ongoing problem with solid waste burial in terms of creating water quality problems in groundwater. There have been, in modern construction standards, liners and more effective caps, leachate recovery systems, and systems to prevent this. But we still have, with aging landfills, throughout the United States at least, serious water quality problems locally in groundwater associated with leachate releases from landfills. There are many, many other water quality problems out there. The book covers some of those, but these are the primary ones I want you to be familiar with. So you should complete the quiz for this segment and move on to preparing for the first exam.